From space, Earth looks calm, a blue and white marble. But beneath that calm, our planet is alive with motion. Colossal forces shape continents, raise mountains, and carve ocean trenches, driving the evolution of our world. Earthquakes are the most dramatic signs of this restlessness, striking without warning and transforming landscapes in moments. Ancient peoples saw them as acts of gods, but science has revealed their true cause, the shifting of the planet's crust. Understanding earthquakes is essential for our safety and survival. Seismology, the science of studying these vibrations, lets us peer into the planet's hidden interior. Seismologists act as detectives, using faint tremors to map the unseen world beneath our feet. Their work helps us build safer cities and prepare for future quakes. This is the story of human ingenuity confronting the immense power of nature. Welcome to the Restless Earth. Seismology is the scientific study of earthquakes and the powerful forces that shape our planet from deep within. It's a branch of geophysics that helps us understand not only why the ground shakes, but also how the Earth's crust is constantly changing, sometimes in dramatic and destructive ways. At its core, seismology explores the energy waves released during an earthquake, waves that travel through the ground, sometimes shaking cities and landscapes miles away from the source. Imagine dropping a stone into a still pond. The ripples that spread out are much like the seismic waves that radiate from an earthquake's epicenter, traveling through solid rock and soil, carrying energy outward in all directions. To detect these subtle and sometimes violent movements, seismologists use sensitive instruments called seismometers. These devices are so precise they can pick up vibrations from distant earthquakes or even the faint tremors caused by a passing truck. When an earthquake strikes, seismometers record the shaking as a seismogram, a visual trace that captures the Earth's pulse, showing the intensity and duration of the event. These records are crucial for understanding the nature of each quake, but seismologists do much more than just record earthquakes. They analyze seismic data to pinpoint where a quake began, how deep it was, and what caused it. Their investigations help us understand the hidden processes beneath our feet. Most earthquakes are triggered by the slow, relentless movement of tectonic plates, the massive slabs of rock that make up the Earth's surface. Where these plates meet, they grind, collide, and sometimes slip past each other, building up stress over years or even centuries. When the stress becomes too great, the rock suddenly breaks, releasing energy in a powerful jolt. This release sends shockwaves through the ground, causing the shaking we feel during an earthquake. By mapping plate boundaries and fault lines, seismology reveals the dynamic forces that are constantly reshaping our world, from the highest mountains to the deepest ocean trenches. Seismology isn't limited to earthquakes. It also studies vibrations from erupting volcanoes, massive landslides, and even human activities like mining explosions or underground nuclear tests. Each source leaves a unique signature in the seismic record. By analyzing these waves, scientists can monitor natural hazards, enforce international treaties, and even explore remote places like Antarctica, where seismic stations help us learn about the planet's most extreme environments. In the end, seismology gives us a unique window into Earth's powerful processes, helping us prepare for disasters, understand our planet's history, and appreciate the restless energy beneath our feet. The secrets of the Earth are carried by seismic waves, vibrations that travel through the ground, whispering stories from deep within our planet. These waves are not just tremors, they are the language of the Earth, revealing what lies beneath our feet. Each seismic wave moves with its own unique speed and motion, creating a complex symphony of energy that scientists work tirelessly to decode. Some waves race ahead, while others lag behind, each carrying vital clues about the Earth's structure. When an earthquake strikes, it unleashes a burst of energy that radiates outward in all directions. This energy travels as body waves, which move through the planet's interior, and as surface waves, which ripple along the crust, shaking everything in their path. Surface waves, in particular, are responsible for the dramatic ripples and cracks we see on the ground during a quake. Their movement can be slow and rolling, or sharp and jarring depending on the type of wave and the materials they pass through. Body waves, known as P waves and S waves, arrive first and are the fastest travelers. P waves compress and expand the ground, while S waves move it side to side, both racing through the Earth's layers at incredible speeds. Surface waves follow after, moving more slowly but with far greater destructive power. These waves are often responsible for the most severe damage to buildings and infrastructure, as their energy is concentrated near the surface. By carefully comparing the arrival times of these different waves at seismic stations around the world, seismologists can pinpoint the exact location of an earthquake's epicenter, often within minutes of the event. This rapid analysis is crucial for emergency response teams, allowing them to quickly assess the situation and deploy help where it's needed most, potentially saving countless lives in the aftermath of a disaster. As seismic waves travel, they bend, reflect, or slow down depending on the materials they encounter: solid rock, molten magma, or dense metal. These changes in speed and direction act like fingerprints, revealing the hidden composition of the Earth's interior. Like a planetary CT scan, seismic data allows scientists to build detailed 3D models of the Earth's inner layers, mapping everything from the crust to the core without ever drilling deep underground. Over decades, seismologists have pieced together a remarkably detailed model of our planet's interior, using only the echoes and vibrations recorded on their instruments and never seeing these layers directly. Seismic waves are our messengers from the deep, carrying information from places we can never visit and helping us understand the forces that shape our world. They tell the story of a world in constant motion, where continents drift, mountains rise, and the Earth's restless energy is always at work beneath our feet. The first seismic waves to reach us after an earthquake are called P waves, or primary waves. These are incredibly fast compressional pulses that move by pushing and pulling the material they travel through, much like a slinky toy being stretched and compressed. P waves are unique because they can travel through all states of matter: solids, liquids, and even gases, making them the most versatile of seismic waves. Their speed and ability to move through the entire planet make them the first messengers from deep within the Earth, carrying vital information about the layers they pass through. Hot on the heels of the P waves are the S waves, or secondary waves. These waves move the ground side to side, shaking rocks and soil in a motion that's perpendicular to their direction of travel. Unlike P waves, S waves can only move through solids. They're completely blocked by liquids. This difference in behavior is crucial, as it helps scientists distinguish between the various layers hidden beneath our feet. When scientists noticed that S waves disappeared in certain regions after an earthquake, it was a groundbreaking discovery. The absence of S waves in these so-called shadow zones revealed that part of the Earth's interior must be liquid. This led to the realization that our planet has a liquid outer core, a revelation that forever changed our understanding of Earth's structure. P waves, although able to cross the core, don't travel in straight lines. As they pass through different materials, they are bent and slowed down, creating their own unique shadow zones on the opposite side of the planet. These distortions in their paths provide further clues about the composition and state of Earth's inner layers. By carefully tracking where both P and S waves appear or vanish, scientists can map the boundaries between the crust, mantle, and core. Each wave's journey is like a signal bouncing off invisible walls, outlining the hidden architecture of our planet. These seismic waves act as our probes into the deep Earth, allowing us to explore regions that are otherwise completely inaccessible. With sensitive instruments placed around the globe, we can listen to the echoes of earthquakes and decode the secrets they carry. The way these waves speed up, slow down, or disappear altogether lets us measure the thickness and composition of each layer with remarkable precision. Seismology has become a powerful tool, giving us a detailed map of the Earth's interior without ever having to dig deep beneath the surface. Thanks to these discoveries, seismology has transformed the invisible depths of our planet into a mapped reality, revealing a world that was once hidden from view. Every earthquake is like a new experiment, sending out waves that help us refine our understanding of the planet's heart. Each tremor adds another piece to the puzzle, making our picture of the Earth's interior ever clearer. The Earth's interior is no longer a complete mystery. It's a dynamic, layered world that we can now explore, study, and understand, thanks to the remarkable journey of seismic waves. When seismic energy reaches the surface, it creates surface waves, the true shakers. Love waves move the ground side to side, damaging building foundations. Rayleigh waves roll the ground in an elliptical motion, like ocean waves, causing intense shaking. These waves arrive after the body waves but do the most damage, toppling structures and breaking roads. Engineers study surface waves to design buildings that can flex and survive. The largest, longest-lasting waves on a seismogram are usually surface waves. Understanding them is key to protecting lives in earthquake zones. Surface waves turn deep energy into real-world destruction. Seismology has mapped the Earth's interior, without ever drilling deep. The first big discovery was the MOHO, the boundary between crust and mantle, found by tracking how seismic waves speed up in denser rock. The S-wave shadow zone proved the existence of a liquid outer core. Inga Lehmann's work revealed a solid inner core, hidden within the liquid. Today, seismic tomography, like a CT scan, uses thousands of earthquakes to build 3D images of the mantle. We can now see plumes of hot rock rising and cold plates sinking, visualizing the engine of plate tectonics. Seismology transformed our view of Earth from a simple sphere to a dynamic, layered system. Every quake adds detail to this invisible map. The deep Earth is no longer out of reach. Human curiosity about earthquakes is ancient, but scientific seismology began in China with Zheng Heng's ingenious earthquake detector in 132 CE. The 1755 Lisbon earthquake shattered old beliefs and sparked a search for natural causes. The 19th century saw the invention of seismometers and the birth of data-driven earthquake science. Robert Mallet coined the term seismology and pioneered wave experiments. After the 1906 San Francisco quake, Harry Fielding Reid's elastic rebound theory explained how stress builds and snaps along faults, releasing seismic energy. This theory remains a cornerstone of earthquake science. Seismology evolved from myth to measurement, forever changing our understanding of the restless Earth. Each discovery brought us closer to predicting and surviving earthquakes. Today, seismology is vital for public safety and modern life. While we can't predict the exact moment of a quake, hazard maps show where shaking is most likely, guiding building codes and city planning. Earthquake engineering uses seismology to design structures that withstand tremors, saving lives. Seismology powers tsunami warning systems, detecting undersea quakes and alerting coastal communities in time to evacuate. The science also helps find oil and gas, and monitors for nuclear tests, supporting global security. Seismology's reach extends from disaster prevention to resource discovery and arms control. It's a science that keeps us safe in more ways than one. Our world depends on listening to its heartbeat. Seismology is a testament to human curiosity and resilience. It shapes how we build, where we live, and how we prepare for disaster. The same science that protects cities on Earth is now used to study quakes on the Moon and Mars. Seismology connects us to the immense power and beauty of our planet. By listening to Earth's heartbeat, we protect ourselves and deepen our appreciation for the forces that shape our world. It teaches us humility before nature and confidence in our ability to understand it. The restless Earth is our home, and seismology is our guide.